Hello, welcome to the course UEC 001. Let's begin this module with the component PIV rating of half wave rectifier. PIV rating is nothing but the maximum amount of voltage appears across the diode when it is reverse biased such that diode can handle that voltage safely. Okay, so in case of half wave rectifier, we have to check the maximum amount of voltage appearing across the diode when it is reverse biased. Okay, I'm drawing the circuit diagram which we have used for the complete analysis of half wave rectifier. So we have used one transformer, and I'm creating the situation of reverse biasing of diode. Load resistance RL. So suppose this is my input signal across the primary, and we have mentioned that this is my terminal M, this is my terminal N, and voltage across the secondary peak value Vm that we have assumed and performed the analysis. And now I have to check voltage across here. So I'm saying that this is my V dash, the open circuit voltage here. Okay, and this is my load voltage RL. So if you can recall that terminal M should be negative and terminal N should be positive so that the diode will be reverse bias. Okay, so I'm interested to find the value of V dash. Okay, now you can check, as this is the open circuit, that means the value of current, the value of current in this particular circuit I will be equals to 0, and as current I equals to 0, therefore voltage across RL, voltage across RL will also be 0. Hence, whatever be the peak value across the secondary, this voltage appears across the open circuit terminal. Hence, V dash is equals to Vm. That means whatever be the peak value or maximum value we are having across the secondary will appears across the V dash. So what should be the PIV rating? So my PIV rating should always be greater than or equals to this voltage. Therefore, my PIV rating Vm. Okay, so this is the analysis for half wave rectifier PIV rating. Now let us see few drawbacks of half wave rectifier and refer the term. This is the first one, ripple factor. Ripple factor is too much, 1.21, and the second thing is rectification efficiency. So you can check rectification efficiency is 40.6%, and in fact it is clear from the waveform. If you can see that for one half cycle there is no output, that means there is a wastage of, from this waveform one can see that there is a wastage of 50% of power. However, mathematically it is more than that. We have estimated the efficiency and it is 40.6, so approximately 60% wastage of power is there. So what is the solution? So solution is full wave rectifier. Okay, centrally tapped full wave rectifier. So let's see the circuit. The transformer is there, and this is a special type of transformer where the secondary winding is centrally tapped. So meaning that the voltage across the secondary is equally divided into two halves. So it is having the upper segment of secondary and lower segment of secondary. So one has to choose this common point such that the overall voltage of secondary winding should be divided into two equal halves. So in fact that is the precaution which designer have to take while designing this center tap transformer. So in this diagram we have taken Vm is the voltage across half of the secondary. Second thing is two diodes have been required. If you compare the circuit with half wave rectifier where we have used only one diode, here we require minimum two diodes, and my second requirement over here is both diodes should be made up from the same material and having the same characteristics, and then the load resistance RL is connected, across which we want to check the output voltage. Okay, so this is the circuit diagram. Now for the working of this circuit, I am further drawing the two segments for positive half cycle and negative half cycle for the better understanding. Okay, so the working of centrally tapped full wave rectifier is shown in part A and part B. So in part A, we have selected the input signal for 0 to pi, that is for positive half cycle, and in part B, we have selected for pi to 2 pi, that is for negative half cycle, for negative half cycle. Initially, we have assumed that my both diodes D1 and D2 are ideal. Now you can check. For positive half cycle, terminal M is positive with respect to terminal M. And as I have already told you that in this rectifier, we require a central point. So the upper terminal of secondary winding is positive with reference to the central point. Okay, so I'm saying that I'm having a VM voltage. So this makes terminal M positive connected to the anode of the diode D1, whereas negative polarity is connected to the anode of diode D2. That means uh, diode D1 will be replaced by a closed switch and diode D2 will be replaced by an open switch. That means the lower portion of the secondary of the transformer is open circuited, whereas the upper portion is closed circuited. And this is the flow of current which I have shown. So I am saying that this current I is flowing and I have to find this voltage V naught. Okay, I have to find this voltage, in fact V out, because I have shown in the characteristics V out voltage over here. So this is the load voltage. The peak value across the load resistance is Vn, which we have shown over here. Okay, if suppose I'm assuming that my diodes are made up from silicon, if I'm taking the practical condition, then you can check the difference will be like this. Now just I'm showing the value of initial value of Vm. This is I'm showing the initial term of Vm, and the actual output curve will be this, as I have shown earlier in case of half wave rectifier. So this will be offset, and this offset will be due to zero point 0.7, and now the peak value is Vm minus 0.7 volt. So this is the situation when D1 and D2 both are made up from silicon. So I have shown the practical curve also. So this is the working for positive half cycle. Now let us see the behavior of circuit for negative half cycle. So you can check in figure 2, I have shown the negative half cycle in the input side. Therefore, my terminal M is negative with reference to terminal N. Okay, so polarity will be minus plus minus plus I have shown. Now you can check my diode D1, which is connected to the upper part of the secondary, will be open circuit and replaced by open switch. However, diode D2, the part uh, of lower portion of the secondary, it is now closed switch. So there will be no current flow in the upper part. However, in the lower segment, there will be a flow of current. And as per the polarity, I have mentioned the direction I. And voltage across the load resistance will be V out. Okay. So again, for the condition, which is my ideal condition, I have shown the curve. interesting part over here is you can check my input signal was negative half cycle pi to 2 pi, but I have shown the output in the positive portion. So you can check the polarity of voltage across the load resistance and net flow of current. So in both the half cycle, current is coming towards the central point O. Okay, that means in both the situation direction of current is unique. So I'm summarizing over here. Direction of current is same in both the half cycle, in both the half cycles, and this is very very important. As the direction of current is same, therefore you can check for positive half cycle from 0 to pi, I am having positive waveform, and for negative half cycle from pi to 2 pi, still we are having a positive outcome. Okay, so this is the working. For the case of practical case, the waveform will be similar. Okay, so in general I have shown over here the one case of the practical scenario. So this is the overall working of my center tap full wave rectifier. Now let me draw the circuit diagram first. Okay, so now you can see the circuit diagram of bridge full wave rectifier. You can check in this circuit we are using the normal transformer which we have used in the half wave rectifier. Secondly, you can check we require over here 4 diodes. We have used over here 4 diodes. So you can see there is one comparison. In case of half wave rectifier, we have used 1 diode. In centrally tapped full wave rectifier, we use 2 diodes. However, in bridge rectifier, we are using 4 diodes and one load resistance, and we have to find the output voltage across this load resistance. So first, uh, there is a question that what is the significant difference between centrally tapped full wave rectifier and bridge full wave rectifier? So as far as the output waveform concerned, output waveform will be similar in case of both centrally tapped full wave rectifier and bridge full wave rectifier. But the designing, the more accuracy in the designing of central tap transformer is required in case of CTFWR. If accuracy in the design was not considered, then there may be a chance either upper portion of the half of secondary or lower portion of the half of secondary will not have the equal voltage and output will not be stable. So to avoid such situation, one can use the full wave bridge rectifier. So for the working of bridge full wave rectifier is shown in part A, sorry, part 1 and part 2. So here we have assumed that for the simplicity when all 4 diodes are ideal and having the same characteristics. Further, the peak value across the secondary of the transformer is Vm. So for the positive half cycle, part 1 is indicating that terminal M is positive with respect to terminal N. Therefore here terminal A is positive and C is negative. Now you can see from the main figure, as terminal A is positive and C is negative, therefore diode D1 and diode D3, these two will be forward biased because the anode of D1 is connected to the positive terminal and cathode of D3 is connected to the negative terminal. So D1 and D3 will be conduct, that means on. However, D2 and D4 will be off. So we have shown the same on the first part of the figure, and I have mentioned in the figure that is for the first positive half cycle 0 to pi, for 0 to pi interval for first positive half cycle, that diode D1 and D3 are on and D2 and D4 are off, as these two are forward biased, whereas D2 and D4, these two are the reverse bias. And as far as the flow of current through the load resistances, so as terminal A is positive, so I am marking the direction, Current will flow from A to B first, then B to load resistance D to C terminal, and to the amp. Okay, so this will be the flow. That means current is flowing from B to D. Okay, so current is flowing from B to D. Okay, so this is the direction. So I have mentioned the output waveform over here where Vm is the peak, as I have assumed that all diodes are ideal. Interesting, negative half cycle, that means from pi to 2 pi. So I have mentioned the same diagram in the input cycle over here, and you can check the Vm is the peak voltage across the secondary. Now terminal M is negative with respect to terminal N because we are working here in negative half cycle of the input signal. So A is negative with respect to C. Now reverse action will take place. You can check over here in the main figure. Anode of D2 is connected to the positive terminal and cathode of D4 is connected to the negative terminal. Therefore diode D2 and D4, these two will be on. However, diode D1 and D3, these two will be off. Okay, so I have mentioned in the figure 2 part over here. Now interesting part is the flow of current. So you can check the flow of current, as my terminal C is positive, therefore current will flow from C to B and then through this load B to D, D to A, and to the inside. So now you can check the direction of current is same, means irrespective of the half cycle, whereas we are dealing to positive half cycle or negative half cycle, the flow of current through the load resistance is constant. That means the voltage across the load, okay, will have the same polarity in both the cases. So you can check in the output formation. I have shown the positive waveform over here from pi to 2 pi. Okay, and peak signal is Vm because we have considered the ideal scenario over here. So you can check, even though my input signal is completely negative signal, but at the output I am having the positive waveform. So second thing is it necessary that for all the rectifiers we have the positive waveform at the output? So answer is no. It will depends upon the direction of the diode. If you invert the direction of diode in all the circuits which we have discussed in half wave rectifier, centrally tapped full wave rectifier, and bridge full wave rectifier, then you will find that at the output you will get the negative waveform. So this is a sort of exercise that you can try, and you can see the working for all these cases. Now let me do one important part over here. What will happen if all diodes are practical? So for that case I'm just assuming one term, that all diodes are made up from silicon. All diodes are made up from silicon. Then what will happen? And I want to show the waveform what will be the difference. So I'm showing for one particular half cycle, and the same will be applicable for both. So if this is my Vm, I'm showing over here for output for 0 to pi, I'm showing over here. Now you can check in any loop. If all diodes are practical and made up from silicon, so rather than replacing by a short circuit, they will replace by a battery of value equals to 0.7, because silicon have a threshold voltage of 0.7 volt. And you can check for any loop, minimum two diodes have been there. That means there will be a significant difference, like my practical waveform will be somewhere this. These are the offsets just because of the cut-in voltage, because minimum 0.7 voltage is required over there. And now you can check there is a significant difference between these two. And now this is my Vm minus zero point 0.7 for one diode, minus zero point 0.7 for another diode. That means the peak value over here is, my peak value is Vm minus 1.4. This is very much interesting. So effective peak value for the practical situation for a bridge full wave rectifier is Vm minus twice of Vk, where Vk is the threshold voltage. It will depends upon the type of material used for the PN junction diode. Okay, so I'm shading the reason. My actual waveform is this, which we will have. Okay, so this is the working of bridge full wave rectifier. Now let us see the waveform. So you can check, I have taken the input signal of peak value plus minus Vn. Okay, and interesting point over here is, which I have highlighted, in case of centrally tapped full wave rectifier, the assumption is the peak value of Vm is nothing but this is for half of the secondary. Whereas in case of bridge full wave rectifier, I have mentioned that my signal Vm is the peak value of the complete secondary. Okay, so this is a major difference, and with these two cases, one can easily understand the respective output waveforms. So you can check the output waveform, and I have also mentioned that these waveforms are valid for the ideal cases only. Like for centrally tapped full wave rectifier, D1 and D2 both are ideal. However, for bridge full wave rectifier, all four diodes D1, D2, D3 and D4, they are ideal. So now you can check for output waveform is same for both centrally tapped as well as bridge. Okay, so I have not mentioned, this is the common waveform for all. Now this is the voltage waveform. In order to find the value of load current, so we can check my load current is also same for 0 pi, 2 pi, 3 pi and here 4 pi. Interesting part over here is the peak value, and now peak value will be of Vm divided by the load resistance. Okay, so for ideal situation, my peak value of load current is Vm by RL. The important point over here is the voltage across the diode. So here I have shown the two waveforms for separately for the center tap full wave rectifier and for bridge rectifier, and I have mentioned twice Vm, peak value is twice Vm for the center tap. However, peak value Vm, and this is the voltage across an single diode. Okay, so this is the voltage across single diode. Now let me explain, and starting with the centrally tapped full wave rectifier. So we can check, suppose I am choosing the first circuit for positive half cycle. So we can check in this positive half cycle, the voltage across diode D2. The voltage across diode D2 over here is, if you can check over here across diode D1, then it will be 0. But here I am showing the voltage across diode D2. So you can check in this situation, it is Vm plus this Vm. Vm plus this Vm. So you can check now Vm plus Vm means 2 Vm. So positive, uh, so maximum voltage across this diode is negative, and which is of value twice Vm. Okay, so I'm mentioning over here, this is the voltage across diode D2 for positive half cycle. This is for diode D1. This is for diode D2, and this is for diode D1 combined waveform. Now you can check the peak value of voltage across a diode for bridge rectifier. Now we can refer this. Suppose taking for the positive half cycle, now you can check D1 and D3 both are forward bias, so voltage across these two will be 0 in this positive half cycle. Now we have to check the voltage across diode D2 and D4. So now you can check, as these two are short circuited. If this is short circuited and this is short circuited, so voltage across B and C is nothing but voltage across RL. As terminal C and D are combined and terminal A and B are coincides, so as these two are coincides, so we can check the voltage across the open circuit of diode. Now it is my, so I have shown the peak value over here, and this is my Vm. So this is the voltage across diode D2 and D4, and this is across D1 and D3. So similarly, one can have this. And practical scenario I have already mentioned. So in case of the practical term, there will be a significant difference. And what is the difference? Assuming that all diodes are made up from silicon. So if all are made up from silicon, then I will have this type of waveform I have already shown over there, we will have some offsets. Okay, interesting part is this peak, and this peak is Vm minus zero point 0.7 for CTFWR, whereas this peak is Vm minus 1.4 bridge FWR. And reason you must know, in case of center tap full wave rectifier, in a single loop there is one diode. However, in case of bridge rectifier there are two diodes. Okay, and if we are considering resistances of diode as well as secondary, then I can mention the value of current waveforms also. Okay, so these will be the waveforms of current, and the peak value for current for both I am mentioning here Vm minus zero point 0.7 divided by RL plus RF plus RS. This is for centrally tapped full wave rectifier. This is the peak value of current for center tap full wave rectifier, and I am mentioning, in order to avoid the confusion, I am mentioning over here it is Vm minus 1.4 divided by Rs plus 2Rf. So why it is 2Rf? Because in a single loop there are two diodes. So the forward resistance of both diodes has to be included, plus Rs. And this is the peak value for bridge full wave rectifier. So this is the difference, and likewise we will have the difference over here also. Okay, so it will be twice Vm minus 1.4, and likewise it will be Vm minus, sorry, it is twice Vm minus zero point 0.7 and it is Vm minus 1.4. Okay, so these are the input and output waveforms of full wave rectifier. Now let us discuss various parameters. So let's starting with the DC voltage. I will not do the derivation here because I have already given you the idea, okay, how to do the complete derivation. But, and this is for full wave rectifier, irrespective of central tap and bridge, both will be same over here. So VDC, or it will be equals to V average. So I'm just writing the formula. It is 1 upon pi integration from 0 to pi V d omega t, where V is the instantaneous value of my input signal, and I'm saying that my V equals to Vm sine omega t. Okay, so if you put all these things, then I am directly writing the formula that in order to solve this, we will have VDC equals to twice Vm upon pi. So you can prove it by simple algebra. Now the value of VRMS, root mean square, as you can see that my output is still the pulsating waveform, not the pure waveform. So there will be some AC signal mix in the output, so we must ensure the RMS value. So again I am writing the formula first. So it will be 1 upon pi 0 to pi V square d omega t whole raised to power 1 by 2. Why I am taking the period 0 to pi? So you can check in the waveform, my output signal is a periodic signal whose fundamental period is from 0 to pi only. Okay, so therefore I was taking over here the range from 0 to pi. And if you solve this relation, then you will have Vrms equals to my Vm upon square root 2. So Vrms equals to Vm upon square root 2. Now I'm coming to the next point. So similarly, you can calculate the value of currents also. In fact, I can write the value of IDC will be equals to twice Im upon pi, and I RMS equals to twice, sorry, it is my Im upon root 2, Now I'm just giving you the relationship between Im and Vm for centrally tapped full wave rectifier and for bridge rectifier, and I will show you the practical situation over there. So this is for the ideal case. These relations are valid for ideal case. For practical situation, I'm mentioning over here for CTFWR and bridge full wave rectifier dealing with the silicon diodes. When all diodes are silicon diodes, then VDC will be equals to twice into Vm minus zero point 0.7 divided by pi, and V RMS equals to Vm minus zero point 0.7 divided by square root 2. Likewise, over here, this VDC will be equals to twice Vm minus 1.4 divided by pi, and VRMS equals to Vm minus 1.4 divided by square root 2. And relations for their voltages and current I'm writing over here. For center tap full wave rectifier, the current Im equals to Vm divided by Rs plus Rf plus RL. Over here, Rs is the resistance of half of secondary, and if some voltage is given, then it is Vm minus zero point 0.7. So it is Vm minus 0.7 divided by this. Likewise, for bridge full wave rectifier, I'm writing current Im equals to Vm minus 1.4 divided by Rs plus twice Rf plus RL. Over here, my Rs is the resistance of secondary of transformer. Secondary of the This is the resistance of the secondary of the transformer. Okay, so this is the difference, and twice RF because there will be two resistance in the forward direction. Now let us calculate another component, and it is my ripple factor. So if you can recall that formula for ripple factor, it is square root Vrms upon Vdc whole square minus 1, and here I am just considering the ideal case. So my Vrms is Vm by root 2, and Vdc equals to twice Vm by pi. So if I am putting over here, so my Rf equals to square root of Vm upon square root 2 whole square divided by twice Vm upon pi whole square minus 1, and this quantity becomes now Vm, and Vm will be cancelled out, and it will be now pi square divided by 8 minus 1, and this quantity will come up 0.48. So you can check. Now on the similar side, let us discuss the uh, rectification efficiency in the different terms. So my eta will be equals to PDC upon PAC multiplied by 100 in terms of percentage, where my PDC is IDC square into RL, and PAC is I RMS square into R. Okay, so this is for general case, for the ideal situation. So for ideal situation, now in fact I can write the value IDC will be equals to twice Im upon pi, and I RMS equals to Im upon root 2. So my eta will be equals to twice Im upon pi whole square multiplied by RL divided by Im upon square root 2 whole square into RL. So now you can check this RL and RL will be cancelled out. Im square and Im square will be cancelled out. 2 square 4 multiplied by root 2 square 8 divided by pi square. So my eta over here is, it is pi square by 8. So if you solve and in fact I forget to multiply by 100, multiplied by 100, so my eta will be equals to 81.6%, which is double of half wave rectifier. It is double of half wave rectifier. This is now the next is, let us see for this for CTFWR, for centrally tapped full wave rectifier, and I'm considering the practical situation. So in that case, the PDC will be IDC square into RL, and PAC becomes now I RMS square into RS plus RF plus RL. So my eta I am directly writing over here. It should be 0.816 divided by 1 plus RS plus RF divided by RL. That means in case of centrally tapped full wave rectifier, the maximum efficiency is 81.6%. But if you consider all the practical things, then it will be lagging somewhere from this. Now I am mentioning over here for bridge full wave rectifier, and you can check PDC for this is IDC square into RL, and PAC is I RMS square into RS plus 2RF, because there are two resistances in a single loop and RL. So my value of eta will be equals to 0.816 divided by 1 plus RS plus 2RF divided by RL. This is the efficiency for bridge full wave rectifier. Okay, so these are the practical situations I have discussed with you. Okay, so this is all about for the full wave rectifier. Okay, bridge as well as center tap. Let us discuss the PIV rating quickly. Okay, so PIV ratings, PIV ratings for both. So quickly I'm drawing the circuit diagram of both center tap and bridge, and quickly calculate the PIV rating. I'm mentioning over here considering the positive half cycle case. This is my load resistance. Okay, so terminal M and terminal N, this is positive with respect to N. This is my VM, this is my O, so VM will also be here. AC input signal is there. Now if you can check diode D1 and diode D2, and this is my load resistance RL. So now you can see there is no voltage, okay, because this is short circuit. Plus minus plus minus and plus minus. So you can check, I want to calculate this V dash voltage across a diode D2, because this is open circuited and my PIV rating is greater than to the voltage, maximum voltage which appears across this diode. And if you can check, so from the upper portion of the half of secondary, what you can see that there is a current, and what is the value across this load resistance is Vm. So now you can check v dash equals to vm and plus this vm, that means twice vm. So v dash equals to twice vm, therefore piv ratings for ctfwr, this is for my ctfwr, piv rating for ctfwr should be greater than or equals to twice vm. Circuit, this is my bridge full wave rectifier, and I have shown this circuit for positive half cycle. So you can check D1 and D3 are forward bias, D2 and D4 these are reverse bias, and I want to calculate the voltage across the maximum voltage across the diode when it is reverse bias, and I am saying that this is V dash. So now you can check a and B are coincides, likewise D and C are coincides. So voltage across the open circuit will be nothing but the voltage available across the resistance. And you can check the voltage across resistance peak value is Vm, which is available across the secondary of the transformer. Therefore, over here value of V dash equals to Vm. Hence, my PIV rating for bridge full wave rectifier is greater than or equals to Vm. It is greater than or equals to Vm. Now, quickly I am doing the comparison of all the rectifiers which we have performed. Okay, comparison for all the rectifier. I am writing over here half wave rectifier, CTFWR, and bridge full wave rectifier. So let us discuss starting with the VDC. So VDC for half wave rectifier is, it is simply Vm upon pi. For center tap full wave rectifier, twice Vm upon pi. For bridge, twice Vm upon pi. RMS voltage, VRMS. So for this it is Vm by 2. Over here it is Vm by root 2. Vm by root 2. What about the ripple factor? The ripple factor, it is 1.21, 0.48, 0.48. For rectification efficiency, rectification efficiency, it is over here 40.6% the maximum value, 81.2% the maximum value, 81.2% the maximum value. In fact, I am writing their practical values also so that one can easily calculate. 0.406 divided by 1 plus RF plus RS divided by RL. Likewise, 0.812 divided by 1 plus RS plus RF divided by RL, and 0.812 divided by 1 plus RS plus twice RF divided by RL. Now, in next important point is, which is very important, PIV ratings. So for PIV ratings, half wave rectifier is Vm greater than or equals to Vm, greater than or equals to twice Vm, and greater than or equals to Vm. Number of diodes required, number of diodes required, only one, minimum two, and minimum four. And output frequency, same as of input, double to the input, and over here double to the input. So for this, for the last parameter, you can refer the input output waveforms. So this table, this comparison table will help us for the solving of numericals. Okay, thank you.